Hey everybody, this video lesson is on solubility equilibrium, or the idea of KSP. It's an equilibrium constant for dissolving. You can find a copy of these blank notes on our Schoology page. It might be a good idea to have these notes because the practice problem, the practice FRQ that I'm going to do, can be uploaded into Notability and then you can do it along with me. There's a small section in the textbook about solubility product. It's chapter 17.4 on page 722. And as I mentioned, this is an equilibrium concept. Equilibrium expressions can be expressed in three different ways: Kc for concentration, Kp for pressure, or Ksp for something that is dissolving. Now if we generate a solubility expression for an ionic substance, we'll call it AB. The substance AB is breaking down into A plus and B minus, both of which are aqueous. Now the equilibrium expression, remember, is the concentration of products over the concentration of reactants. And in this case, it's the concentration of A plus and B minus. But the denominator in this case, because it's a solid, does not happen to be included in the equilibrium expression. Remember, when you're doing equilibrium expressions, only aqueous and gaseous species are in the equilibrium expression. So in the reactants part of the equilibrium expression for KSP, we have just a 1 in the denominator, and oftentimes we don't even write the 1. So to clean it up, KSP is equal to the concentration of the A ions times the concentration of the B ions over 1, or just that's it. And don't forget, if either of these products have a stoichiometric coefficient in front of them, then that's going to be expressed as an exponent in the equilibrium expression. Now a few general comments on the equilibrium expression for solubility, or KSP. First of all, it's assumed that the solution is going to be at its saturated state. Remember, the concept of saturation means that it has the maximum amount of ions that could be dissolved in the amount of solvent that you see in front of you. In fact, you might even see a little bit of undissolved precipitate sitting at the bottom. It's the solid that cannot be dissolved anymore because the solution has taken the maximum amount of ions that it could possibly take. The second thing I want to say is that all of these are temperature dependent. Like all equilibrium constants are temperature dependent, solubility likewise is temperature dependent. So almost always, equilibrium constants for solubility are expressed at 25 degrees Celsius, or standard state conditions. Now a couple of other general observations about KSP. If the number for KSP is much larger than 1, then we consider that a highly soluble substance. And think about that in terms of the math. If you take some AB solid and you put it in and you get lots of ions of A and lots of ions of B dissolving into the solution, then these two numbers are going to multiply together to be a very large number. And if you have a high concentration of A and B in solution after it dissolves, then you have a very high KSP, which means it's very soluble. Now on the other hand, if KSP is much smaller than 1, then we would consider that very insoluble. So take the same example, AB gets put in only a couple molecules compared to the overall amount. Maybe you put 10 grams of AB solid in and you get a couple molecules of A and a couple molecules of B ionizing in the solution, then A times B is not going to be very large, and that number multiplied together results in a very small number. We're talking about like times 10 to the negative 5th or 10 to the negative 10th. Then you'd consider that substance to be very insoluble. Here's a real example of a substance that has a very low solubility. BaSO4, when dropped into the water, only ionizes a very small amount. Now you get some Ba ions in solution and some SO4 minus ions in solution, and so the expression for KSP is Ba plus 2 concentration times SO4 minus 2. And when you multiply the Ba ions times the SO4 ions in solution at 25 degrees Celsius, the concentration is not very large. In fact, you have such a small quantity that the concentrations multiplied together give you 1.1 times 10 to the negative 10th. Now remember, it's an equilibrium constant, so it's a unitless value, but it's very, very small, so you can say that this substance is fairly insoluble. This table in the notes shows you various different KSP values for bunches of different substances here. And as you can see, the KSP values range from numbers that are pretty small, like barium carbonate, which is 5 times 10 to the negative 9th, to things that are really, really small, like copper sulfide, which measures in at 6 times 10 to the negative 37th. So what we can conclude is that these solubility product constants are all very reactants favored. So in other words, products will not be produced at high concentrations. So keep that in mind when you're trying to do calculations involving KSP values. The concentration of the products will be very, very small. I'd like to now show you what one of those calculations might look like. And the first thing I want to talk about is something called molar solubility. And it's defined as the molarity of a saturated solution of any substance that's been dissolved. And the example that I'm going to give you today is calcium fluoride. Calcium fluoride comes in with a KSP value of 3.9 times 10 to the negative 11th at 25 degrees Celsius. And we need to calculate the molar solubility, or in other words, the molarity of the saturated solution. So what we're going to do here is treat this like an ice table. Remember, ice table has initial change in equilibrium. And initially, we have 0 molar calcium ions and 0 molar fluoride ions. And the change is going to be adding plus X, because it's 1 mole of calcium, and adding 2X, or 2 fluoride ions, because it's a 2-to-1 ratio. And if you just add these up, what you get is X and 2X. You might be asking yourself once again, what's with this CaF2 column? Well, remember, in equilibriums, things that are solid and things that are liquid are not included in the equilibrium expression, so we don't even need to worry about them when we're filling out the ice table. Now we're going to plug those equilibrium values into the equilibrium expression, which we don't have written yet, but here it is. It's KSP, which is 3.9 times 10 to the negative 11th, is equal to Ca times F minus squared. Don't forget, F minus is squared because there's a 2 in the stoichiometric coefficient in front of that ion, and so we need to square that value. So let's scroll down here and give ourselves some space so we can execute this problem. So we're going to put X in for this calcium, and we're going to put 2X in for this F minus, and we're going to multiply those together and combine like terms and set that equal to 3.9 times 10 to the negative 11th. Then we're going to use our algebra skills to solve for X. So 2X quantity squared is 4X squared, and we're going to multiply that by X, and what we're going to get is 4X cubed, and set that equal to 3.9 times 10 to the negative 11th. Now we're going to divide by 4 on each side, and that is going to get us X cubed is equal to 9.75 times 10 to the negative 12th. Now I just need to solve for X by taking the cube root on each side, and X is equal to 2.14 times 10 to the negative 4th molar. Since that is the X, that is our molar solubility, or basically what the concentration of the solution is at saturation. I want to finish this video today talking about a couple of things that will affect the solubility of a substance. And this is outlined in Chapter 17, Section 5 in our textbook. The first thing I want to talk about is a situation where you add a common ion to a solution that has limited solubility. Let's take, for example, once again, our calcium fluoride, which we worked with on the last slide. We calculated the molar solubility of the calcium fluoride, but what happens if I add a common ion like either calcium or fluoride to a solution of calcium fluoride? How is that going to change the equilibrium? Well, as you might expect, this is the Le Chatelier's principal concept. If we add a common ion, which are on the product side, either calcium or fluoride ions, it's going to increase the concentration on the product side, and it's going to cause stress on this equilibrium and shift it back to the left. And if we shift back to the left, we decrease the solubility of the calcium fluoride. So adding a common ion is a way to decrease the solubility. Maybe you don't want something to dissolve quite as much, so you add some common ions, and it will shift equilibrium to the left. Finally, I want to talk about what happens to the solubility of a salt when you change the pH. Now, in certain situations, changing the pH can change the ability of a salt to dissolve, and I'm about to explain that now. Now, first of all, you need to have a salt or an ionic substance that is going to have a basic anion, or in other words, the conjugate base of a weak acid. Let's take, for example, one more time, the calcium fluoride equilibrium. Now, when the hydrogen ions come in, they're going to find the fluoride ions, and hydrogen and fluoride is a weak acid. The hydrogen and fluoride will find each other, and then the F- ions will actually become part of the hydrogen fluoride. So essentially, they are being removed from the equilibrium rather than being added. In our last example, adding a common ion shifted the equilibrium to the left because it increases the concentration of the products and it causes a shift to the left. But this time, by introducing the acid, you are taking the F- ions away from the equilibrium, basically removing them and shifting the equilibrium to the right. And as a result, what's going to happen is that the solubility of the calcium fluoride will increase in an acidic solution because the fluoride ions are no longer part of the equilibrium, but they are now bonded to the hydrogen in the form of hydrofluoric acid. Remember, hydrofluoric acid is a weak acid, so hydrogen and fluoride will just exist dissolved in the solution. But the fact that it's not part of the equilibrium involved with calcium any longer means that the stress has been put on the right side, taking away the ions, shifting the equilibrium to the right, and thus increasing the solubility. So in summary, when you add an acid to a salt that has established a dynamic equilibrium, as long as that salt has the conjugate base of a weak acid, solubility will increase. If the anion is the conjugate base of a strong acid, this will not affect it, because when you add hydrogen ions to, say, for example, maybe nitrate, what if the anion was nitrate instead of fluoride? So nitrate is the conjugate base of a strong acid. And when you add acid ions into the nitrate, because nitric acid is a strong acid, it 100% dissociates, so it will not affect the concentration of the nitrate ions in the solution. They'll just kind of exist in the solution as they already were. They will not combine with the hydrogen to form a new substance, and so the concentration of the nitrate ions will remain unchanged, and there will be no shift in the equilibrium when the anion is that of a strong acid. Well, that takes care of this video lesson. Thanks for watching.